So in today's session, we will be explaining an overview of earthing. So some of the concepts which many people had some misconceptions regarding this earthing. So in today's webinar, we will be completely explaining about this fundamentals of earthing and how to select the material for earthing and what are the materials that can be used for earthing. And if I provide only one rod and connected to this equipment, whether it serves a purpose. So today we will be explaining mainly on the fundamental things that are related to this earthing. And if you want to know anything in detail about the earthing for specific applications, we are planning to provide a separate webinar session based on the applications like designing of earthing for substation applications, designing of earthing for industries, and designing of earthing for solar farms. So in the upcoming webinar series, we will be explaining this earthing for specific field. And in today's session, we will be concentrating on overview of the earthing. We will be providing just basic things about the earthing, and we will provide some clarifications regarding the misconceptions in the earthing and what are the materials can be used, what should be the minimum size, and how can I select the material sizing for my particular applications, and whether I can use the same size of electrodes for all the applications. So in today's webinar, we will be discussing about these basic things. And we will be explaining about the various references from the different standards related to this earthing. Before entering into this webinar session, let me provide a small brief introduction about our company. So, CIKIT Electricals and Technologies was incorporated in 2018. So, even though it is a 4 years old company, we are having an experience of more than 17 years in this field of lightning protection and earthing solutions. And we are providing end-to-end solutions starting from the site survey, measuring the soil resistivity on the particular site conditions, designing the earthing like a number of earth electrodes required for one site, and what should be the minimum cross-sectional area of earth electrode required for those particular sites, and what are the materials that can be used for the particular sites. So if you take this material of earthing, we cannot go for the same material in all the soil conditions, because the soil will be different in different areas, and based on the soil condition, the corrosion also will be different. So based on the soil resistivity and the corrosion in that particular environment, we will be selecting the conductor sizing. So if you take a normal transformer of same rating, if the transformer is situated in normal soil conditions and if the transformer is situated in a coastal area, then obviously the sizing of the conductor which I choose in coastal area will be little higher than conductor which I use in normal area, because the effect of corrosion will be much higher in the coastal areas as the salt content in the soil will be little higher. So based on the soil conditions, the conductor sizing will be different. Even though if it is a same application, the conductor size will be different based on the soil conditions. So we cannot go for a general solution. So in the designing, we will be providing number of earth electrodes required for that particular site conditions, and what should be the minimum cross-sectional area of the conductors that can be used for those soil conditions. And we are supplying the materials starting from this earth electrodes and earth enhancing compounds, that clamps suitable for those particular earth electrodes, and we are providing maintenance of earthing as a separate service. Apart from that, we are providing auditing of earthing system. So we are providing end-to-end solutions for both lighting protection system as well as this earthing system. And as I mentioned, we cannot go for a generalized solution for all the site conditions. So we will be providing customized solution for the particular site based on the standard specification. So we will be following different standards for different applications. So we won't stick to the same standard. We will be providing the solutions based on the suitable standard for those particular site conditions. So if you take earthing, so these are some of the earthing standards which we follow. So first one is Indian code IS 3043, that is code of practice for earthing, and BS is British standard 7430. Third one IEEE 80 explains about the earthing for substations, and VL 467 explains about the testing for copper bonded rods. So if you take nowadays, the most commonly used earthing material is copper bonded rods. So UL 467 has clearly explained about the testing procedures for this copper bonded rods and the minimum requirements of this copper bonded rods. So because of the stringent testing methodologies, many people are preferring this UL certification. And IS 62305 explains about this earthing for lightning protection applications, and 62567 explains about this requirement of earthing components. So these are the different standards which we follow for earthing. So the most common thing among the people is, many people will think that earthing is suitable only for industries and commercial buildings, but that is not the case. So if you take ours as example, we are working in offers from morning 10 to 6 or 10 to 7 like that, but after that we are going to home, and we are, all of us are consumers of electric power. So we are, all of us are using this day-to-day electrical equipments, and we are all consumers after our office hours. So this electrical safety is very important to each and every house. So earthing is not only related to all the industries and the commercial complex, it is related to all the houses as well. So earthing is very important for all the houses, because we are using this electrical equipments in day-to-day life, and earthing is very important to ensure the safety of the operating people. So if you take this as an example, in all our house we will be using this 3-pin plug point. So in this 3-pin plug point, one will be phase and another will be neutral, and the third point will be earthing point. So if you observe the plug points closely, if the material, that is, if the any equipment or device, so if any equipment or device is made up of metallic enclosure, so in that particular case only we will be going for third pin, that is earthing pin. If enclosure is made up of plastic material or any other insulating material, so in that particular applications we won't be going for this third pin, that is earthing pin. So the purpose of this earthing pin is, if by accident any live wire makes contact with the enclosure, it diverts this entire energy through the ground through this earthing point. So the size of this earthing pin is made bigger for two purposes. So first purpose is, if the size is bigger, then the resistance will be little lower. At the same time, if I accidentally insert this earthing pin into this phase pin, then the phase will be directly connected to the ground through this earthing pin. That should not happen. It is called as phase to ground fault. So the phase to ground fault should not be happening. So in order to avoid this accidental insertion of earthing point into the phase point, the size of this earthing pin itself is made bigger. So even though if you have provided 3-pin plug point and everything you have used, but if the earthing connection is not taken from your main board to the ground, then the current won't be dissipating. So if you are using this 3-pin plug point, in all our houses we should provide minimum of 1 earth electrode at the main box. So that is how earthing is related to all the houses. So it is not for following the regulations, it is for the safety of the people. So it is for the safety of our family members. So it is mandatory to provide minimum of 1 earth electrode for all the houses. So earthing is not a object that is related to industries, it is related to all our houses. So if you take this grinder as an example, so in earlier days this type of model we have used. So this object is a metallic object. So during working, if there occurs any leakage, current leakage, then that metallic part will become live, and if we touch that, we will be electrocuted. So if you take this toaster, here also the body is metal object. So if I touch that, I will feel the shock. And if you take the motor, all the motor enclosures are made up of metal. So if I touch that metallic enclosure, I will feel the shock. That is, may get electrocuted because of the fault conditions. So in all these three conditions, the current won't flow through the metallic enclosure at all the times. So the current will flow through the metallic object only at specific time, that is during the fault conditions or any abnormal conditions. So the purpose of earthing is to provide a dedicated low resistance path to this abnormal current during the fault conditions to the ground, thereby protecting the people. So that is the purpose of earthing. So earthing is not only related to these industries, earthing is related to all our house. So earthing is important for all our houses. So if you take this as an example, so here we have not provided earthing for this equipment. So if by accident, if the live wire makes contact with this metallic structure, then the metallic enclosure becomes live. So if any person makes contact then the current will be flowing through the metal body. Then in this case, he will be electrocuted. So in the same case, if we are providing earthing, so if I have provided earthing, then the fault current will be flowing through this earthing conductor, bypassing the people, because the resistance of the earthing conductor will be very much lower than the human being. So the current will choose to flow through this low resistance path, thereby bypassing the operator. So hence, by providing this earthing connection, we are protecting these people from being electrocuted. So if you take the number of electrical accidents in India, so it is very much higher than other countries. At the same time, the most commonly observed reason for all this electrocution were the improper earthing. So if you take this any fault conditions, all the current will be dissipated to the ground. So if the loop impedance is much higher, then it will take more time for the dissipation, and at the joint, if there are any loose connections, then the current will be discharged through an arc. So the arc will be produced for closing the path, and if there exists any inflammable materials in that area, it will catch fire. So this loose connection on this earthing path may also result in huge fire accidents as well. So the earthing should be proper, and all the connections should be intact in earthing. So what is earthing? So as I mentioned, during abnormal conditions, so it is not in normal conditions, during abnormal conditions, discharging this abnormal fault current to the ground by providing a dedicated low resistance path. So this is called as earthing. So we are providing a dedicated low resistance path for the fault current to discharge to the ground. So from this thing, we have to identify that earth itself is a conductor. So only we are conducting this energy into the ground. So if it is an insulator, no current will be flowing into the ground. So we are discharging all the current into the ground, which means that earth itself is a conductor. But the resistance will be little higher based on the soil resistivity. And so in the previous examples, we have shown that we are connecting the body of the equipment to the grounding for the safety of the operator. So if I connect the body of the earthing to the earth, then it is called as equipment earthing or body earthing. So here we are connecting the non-current carrying metal works. So the body is made up of, enclosure is made up of metal material, but that is not current carrying. At all the times it won't carry the current. So that is a non-current carrying metal part. So we are connecting the non-metal carrying current part to the ground. That is called as equipment earthing. And the second earthing is called system earthing. So if you take the connecting the neutral of the transformer, so the neutral of transformer won't be will be carrying the current at all the times. So your neutral will be acting as the return path. At the same time, if there occurs any imbalance, then the remaining current will be flowing through this neutral only. So connecting the neutral of the system to the ground will be considered as the system earthing. So here the neutral will be a metallic conductor. It always carries the current. So the process of connecting the current carrying metal conductor of the system to the ground is called as system earthing. So these are the two different types of earthing. And the ultimate aim of providing earthing is to provide safety of the operator. So if I am connecting this equipment body or neutral to earthing, what actually happens? If any current flows through this, then the current will be discharging from this earth electrode into the ground. So if a current of I is flowing through this, then this current will be discharging from this earth electrode into the soil. So here we need to understand that the discharge is taking place from one medium to another medium. Here the earth electrode, which receives the energy, is the first medium, and the soil surrounding this rod is the second medium. So here the conduction is taking place from one medium to another medium, and the conduction is not taking place in the same medium itself. And the discharge will be taking place in the form of concentric circles. So the point near to this earth electrode will be at very high potential, and the point which is far away from this earth electrode will be at very low potential. So if you observe this, the potential at the points very near to the earth electrode. So if you take this is the earth electrode. So the potential at the points very near to this earth electrode is very much higher, and after a small distance the potential drops very rapidly. So since the maximum potential is dropping very near to this earth electrode, we will be providing a highly conductive yet enhancer compound surrounding this earth electrode for enhancing the performance, that is to increase the discharge much faster. We will be providing a highly conductive earth enhancing compound surrounding this earth electrode, because the maximum of potential will be dropping at that particular location only. So we will be providing a highly conductive material at that point. So this difference in potential is called as ground potential, right? So at the time of discharge, the entire ground potential itself will be increasing. So because of this increase in ground potential, there occurs two effects. One is called step potential and another one is called touch potential. So the touch potential is nothing but if I am touching a metallic structure which carries a current, then some part of this current will be flowing through our body. So we need to understand that whenever current flows through any object, there has to be a difference in potential. So if two lines are at the same potential, then there won't, if the same potential is there, means there won't be any current flow. So the primary condition for the current to flow is there has to be a difference in potential, then only the current flow can happen. So if you take birds as an example, if a bird is sitting on 11 kV line, then it won't feel any shocks, and at the moment it touches the any different phase, or if it makes contact with any pillars at the ground potential, then it will get electrocuted. So the main reason for this current to flow is there should be a difference in potential. So if you take this as an example, if any fault current or lightning current flows through this metallic structure, then this point will be at very high potential and our foot will be at low potential. So because of the difference in potential between our foot and our body, the current will flow through our hand and it will enter into the ground. So this is called as touch potential. So for the touch potential to cause harm to our body, there has to be a physical contact. But if you take the second one, that is step potential, there is no need for physical contact itself. Even though if I am standing little away from this location of fault, then in that case also I may feel this electrocution if my two legs are far apart. So one such example is if any transmission lines fall on the ground, if we run or if we walk, then in that case the maximum distance between the 2 foot will be higher. So because of this, the potential difference also will be higher. So in that case, if I jump on only one leg, then only one leg will be making contact with the soil and there won't be any potential difference. So if I jump on those side condition fields, I won't feel the shock. So there won't be any potential difference. Then the current won't flow through this body itself. So for this strip potential to cause damages, there is no need for physical contact also. So the effect of strip potential will be much higher in animals than the human being, because the distance between the 2 foot will be much higher in animals than the human being. So if you take this as an example, the distance between 2 foot is very much higher if we compare the 2 foots of a human being. So the effect of strip potential will be much higher in cattle than the human beings. So for the strip potential to cause damage, there is no need for any physical contact also. So this is how improper earthing will be causing the damage. So in the above images, we have shown that there was no earthing provided, but at the time of fault discharging into the ground potential also will be increasing. So in that condition also, step potential and touch potential will come into the picture. So the primary aim of earthing is to provide safety of the operator. So we need to ensure the safety of the operator who will be working on that equipment. And in the substation designing, the two main important parameters are step and touch voltages. So by providing proper earthing, we have to maintain the step voltage and touch voltages below the tolerable limits. And if you take this system voltage as an example, we are mentioning 230 volt or 240 volt or 400 volt as the voltage levels. So for this voltage levels, this grounding acts as the reference. Based on the grounding only, we will be providing the value of this resistance. So the grounding acts as the reference point for this electrical system. At the same time, so we will be providing protective equipments for earth faults. So for this proper operation of earth faults, the earthing plays a crucial role. So if the earthing is not proper, then the protective equipments won't operate properly. So if the earth loop impedance is much higher, then the current flowing through this earthing conductor will be lower. And if the current is not sufficient to operate this protective equipments, then this protective equipment itself won't operate for this earth faults. So for the proper operation of this earthing equipments, earthing plays a very important role. So for these applications, we need proper earthing. So in this upcoming slides, we will be explaining about how to provide proper earthing and how can we select the material for earthing. So if we take this earthing as an example, it consists of three main components. So the first component is the earth electrode. So earth electrode is the metallic conductor which carries this current. So it will be dissipating the entire energy into the ground. And earth enhancing compound are highly conductive material which we will be replacing the highly resistive soil. So the conductive material used for replacing the highly resistive soil is called as earth enhancing compound. And the third one is proper terminal connection. So if the terminal connection is not proper, then it may result in loose connection, and the loose connection may result in arcing and flashing. So if the arc is happening, because of the arcing, then the resistance, overall resistance will be increasing. So proper terminal connector should be provided. So these are the three important components of the earthing. Now first and foremost thing is the earth electrode resistance. Many people will be asking what will be the suitable earth electrode resistance for this kind of applications. So first thing is we need to understand what is this earth electrode resistance. So if you take this resistance as an example, so we might have come across many resistors in electronic circuits. So this will be the symbol for this resistors. So the resistance of the particular material which we are considering is called as ohmic resistance. So the ohmic resistance is the resistance of all the bodies. So this is a resistor is a compound. So if you take any conductor as an example, so resistance is the property of the material to oppose the flow of current from one end to another end. So if the current is entering into this point, so if the current is traveling through this conductor will be providing some opposition. So that is called as ohmic resistance. So resistance offered by this material to the current flow from one end to another end, the same material. So here the entire conduction is taking place on the same material only. So that is called as ohmic resistance. So there is one more resistance called electrolytic resistance. So everyone might be aware of this battery and cells. So cells are the fundamental component of any battery. So this is how a cell will look like. The earlier cells, that is a primary cell will look like. It consists of two electrodes, and these two electrodes will be inserted into a conductive material called electrolyte. So the electrolyte will be a conductive material, and these two electrodes will be provided. One will be positive, another one will be negative. So in electrolytes, so in this kind of assembly, the flow of charges will take place from one electrode to the another electrode in the conductive medium. So here the conduction is taking place from one medium to the another medium. So this kind of resistance involves the conductor, that is resistance property of the material, that is electrolyte as well. So this is how the earthing is also happening. In earthing also, the conduction is taking place from this earth electrode to the soil. So here the conduction is taking place from this earth electrode into the soil. So conduction is taking place from one medium to the another medium. So since the conduction is taking place from one medium to another medium, the resistance of the earth electrode will be electrolytic in nature. So we cannot consider the resistance of the material. So here the most important medium is the resistance of the medium surrounding the electrode. So in our case, the electrolyte is the soil. So based on the resistance of the soil, the conduction will be varying. So resistance of the soil is the most important parameter in the earth electrode resistance. So here we are considering the electrolytic resistance and we are not considering the ohmic resistance. So the material of the earth electrode does not play a huge role in earth electrode resistance, whereas the soil resistivity plays a crucial role. So which means if I use the copper earth electrode, So I am using the same copper electrode of 3 meter length. So if I install this same copper electrode if in a soil condition of 40 ohmmeter, and if I install the same in another soil condition of 400 ohmmeter. So here the material is same, the dimensions are also same, but since the soil resistivity is different, the resistance of earth electrode will be very much higher in the soil condition of having 400 ohmmeter, because the resistance which we are discussing in earth electrode is electrolytic in nature. The electrolytic resistance mainly depends upon the resistance of the surrounding medium and does not depend upon the resistance of the material. So even though if I provide the same copper earth electrode with the same compounds, then if the resistivity of soil is different, then definitely the resistance of the electrode will be different. I cannot achieve the same resistance value which I achieved at the 40 ohm in 400 ohm, because the soil resistivity is the deciding parameter in earth electrode resistance. So if you take this earth electrode resistance, it consists of three parts. So the first one is the resistance of the material, and second one is the contact resistance of soil and the earth electrode, and third one is the resistivity of the soil. So here, if you consider the length of this earth electrode, along the length only the conduction will be taking place, but all the conductors will be having very low resistance. So if you compare these three parameters, the first two parameters will be negligible. So we won't consider the first two parameters, and mainly the earth electrode depends upon the soil resistivity alone. So the soil resistivity plays a critical role in the performance of the earthing, and it is not the material. And the soil resistivity has depends upon the moisture and salt content on the soil. So if the soil has very good moisture, then the resistivity will be little lower. If it is a dry condition, the moisture content will be very much lower. So if we are measuring this earth electrode resistance or performing the soil resistivity measurement, then we should do this measurement only on this dry period, and we should not do performing this test on the wet conditions or rainy seasons, because the resistance value will be reducing than this normal value because of the moisture content. So whenever we are performing this testing, we should always performing this testing on this dry conditions, because the soil resistivity and resistance depends upon the moisture value. So if the moisture is higher, definitely the resistance will become lower. So these are the two factors which has some effect on the soil resistivity and the earth electrode resistance value. So the standard has already provided some approximate soil resistivity value for different types of soil. So this graph is taken from IS 3043. So if you take this soil resistivity of clay and alluvium soils, it is very much lower. So in the second option, they have provided the lower rainfall. So which means if the rainfall is much lower, the moisture content will be lower. So if the moisture content is lower, then the earth soil resistivity will be higher. So based upon the different type of soils and the moisture content, the resistivity of the soil will be different. The standard has provided a simple table for the different type of soils for different moisture content as well. So it is for normal and high rainfall, and this is for low rainfall. So from this graph, we can observe that the resistivity will be different for different soil conditions, and even for the same type of soil, it will be different for different moisture content in the soil. So if the moisture content is higher, then definitely the resistivity will be lower. So the most important thing in earthing is the corrosion. So if you take the soil as an example, if the resistivity is higher, which means that the conduction is very low. So if the resistivity is higher, which means that the minerals and the salt is little lower. So if there are no minerals and salt in that particular soil condition, then obviously the resistance will be higher. So if there are no minerals and salts, then the corrosion also will be lower. So in the other case, if you take this, resistivity is higher on the particular case. So if the resistivity value is very lower, which means that minerals and salt in that particular soil condition is very high. So because of this minerals and salt, the corrosion also will be very high. So in this, we can observe that if the resistance is lower, then corrosion will be higher. If the resistance is higher, corrosion will be lower. So the resistance and corrosion are inversely proportional to each other. So the table has provided a relationship between soil resistivity and the corrosion. So if the soil resistivity is very much lower, that is in this case less than 20 meter, because if the soil resistivity is less than 25, then which means that the soil has more minerals and salts. So because of this huge composition of minerals and salts, the corrosion rate will be very much severe. So if you take another example, if the resistivity is greater than 100, then in that particular case, the minerals and salts in that particular soil conditions will be very much lower, and hence the corrosion also will be very much lower. So this corrosion and resistivity are inversely proportional. So since we are using this earth electrode directly on the soil, the material selected should have very good corrosion resistance property. So the corrosion resistance property of the material plays a crucial role in the material selections. So earth electrode. So earth electrode is the important part of this earthing assembly. So the purpose of this earth electrode is to dissipate this fault current into the ground. Since it is carrying this huge current, the conductor should be selected in such a way that it should be able to withstand this fault current. So in earlier case, we were using the fuse. Nowadays we are using MCB, but earlier case we will be using the fuse. So the purpose of fuse is it will disconnect the entire electrical system from the other electrical system to protect those equipments during high fault current or short circuit conditions. So how it happens is the fuse will melt if the current becomes greater than the rated current. For example, if I am using this 5 amps fuse, for example, if I am using a 5 amps fuse and if the current becomes 10 amps, then because of the heating, this fuse material will melt and it will disconnect the component from the electrical system. So here what happens is, because of this I squared R loss, that is heating will be produced and this heat will melt the conductor. So same thing will happen for this earth electrode as well. So if I am designing an earth electrode, that is, for example, if you take this pipe as an example, so I am having a pipe of 76 mm dia, and if I provide a 25/6 mm strip as a terminal, so if any huge current comes, then this pipe can withstand this huge current, but the terminal cannot withstand this huge current and the terminal will melt. So while selecting this conductor, we should perform this current carrying capacity and we should use the proper material. So the conductors which we use for earthing should be able to withstand the fault current without getting any damages. So if the terminal itself got broken, then the current won't be passed through this pipe and the current won't be discharged. So the proper sizing should be made. And since we are using it directly on the ground, the corrosion resistance property of the material should be checked. It should be at least, it should have good corrosion resistance property. So if you take aluminum as an example, even though aluminum has very good conductivity, it is not recommended to use for earthing because of the corrosion property. It will corrode much faster. So aluminum is not recommended for this grounding applications. So the corrosion resistance of the material plays a crucial role in the material selection. So the standard has explained about 4 different configurations of earth electrodes. So the first one is the plate earthing, and second one is the rod earthing, and third one is the pipe earthing, and many people will be aware of these 3 configurations. So the standard has explained about one more configuration called strip earthing. So in strip earthing, we will be simply laying the conductor below the ground level. Yeah, actually, the depth will be in terms of 500 mm to 1 meter. So that is how we will be selecting the material. So in strip earthing, it will be commonly used for counterpoise earthing as an arrangement and type B earthing of lightning protection system. So in these applications, we will be simply laying the conductor below the ground levels. So the standard explains about four different configurations, and they have provided this formula for calculating the earth electrode resistance value, which is electrolytic resistance value of all the four different types of earthing electrodes. So the first one is plate earth electrode. So here the earth electrode will be in the form of plate. The standard has provided the minimum dimension is 600 cross 600. Whether my screen is visible? Okay, this one. Okay. Okay, just I will check it, sir. Okay, I'm just checking it, sir. Is it visible now? Okay, sir. So, yeah, okay, sir. Fine. And that my previous slide was visible. This slide was visible, right? So while explaining, have you seen this slide, or I have to explain this slide once again? This earth electrode slide, sir. This curve, the earth electrode. So shall I start from this slide? Okay, fine. Thank you, sir. So if you consider this earth electrode, and the most important point is it should be able to withstand the fault current without any damage. So if I take this pipe earth electrode as an example, so if I'm having a pipe, definitely it will be having the terminal as well. So if I'm having a pipe earth electrode of diameter 76 mm, and if I provide a terminal using 25 by 3 or 25 by 6 mm, so in this case, if any fault current of the magnitude around 30 kA is coming, then obviously the 76 mm pipe will be able to withstand that. But this terminal cannot withstand those huge amount of current. And what happens is this terminal will break. So it will melt and the connection to this earth electrode will be damaged. So in that particular application, even though if the fault current is connected to this earth electrode, at this terminal itself, the conductor to this pipe will be broken and the dissipation will be stopped. So while selecting this earth electrode, I should select the proper material so that even the terminal will be able to withstand the fault current of the electrical system. The fault current withstanding capacity of this earth electrode plays a crucial role. And since we are placing this earth electrode directly on the soil, it should have good corrosion resistance property. So even though aluminum is a very good conductor, because of its poor earth electrode resistance, poor corrosion resistance, we are not recommending this aluminum for earthing applications. So the earth electrode which we are selecting should have good corrosion resistance property. At the same time, it should be able to withstand the fault currents. So if you take the fuse as an example, the fuse protect the components during the short circuit and heavy current by melting. So if the proper sizing is not made, then the terminal will melt and it will isolate this earth electrode from the remaining system. So the dissipation won't happen. So current carrying capacity and the corrosion resistance plays an important role in selecting the material for earth electrode. So the standard has explained about four different configurations. So the first one is plate earthing, second one is pipe earthing, third one is rod earthing, and fourth one is strip earthing. So many people will be commonly aware of these three remaining earth electrode configurations, but the fourth one, that is using the earth electrode in the form of strips. So in this case, the strip will be laid at a depth of around 500 mm below the ground level, and that will be connected to the equipment. So it is commonly used for this counterpoise earthing of transmission towers, and the second application commonly used is type B earthing, that is ring earthing for lightning protection system. So in these two applications, we won't be providing vertical earth electrodes. We will be simply connecting the strips to the equipment, and we will bury the strips at a depth of 500 mm. So if you take this plate earthing electrode as an example, so the standard has provided the minimum dimension is 600 mm by 600 mm, and they have not provided any regulations on the thickness, because if you take this plate earth electrode as an example, the dissipation depends upon the surface area. So the standard has explained the dimension for three different materials. So if you observe this, the surface area will be common for all the three materials, whereas the thickness will be different for different materials. So the standard has considered a thickness of 12 mm for cast iron, and for GI the thickness is only 6.3, whereas for copper it is 3.15 mm only. So they have considered different thickness for different materials only to compensate the effect of corrosion. So if you take this corrosion rate, the corrosion rate of copper will be very much lower, and the corrosion rate of cast iron will be little higher. So in order to compensate this corrosion effect, the standard has considered very high thickness for cast iron and very low thickness of 3.15 mm for copper. So the corrosion plays a crucial role in determining the size of this earth electrode. So if I am going for cast iron, then I have to go for 12 mm thickness. But if I am going for copper, I can go for only 3.15 mm of the same dimension, 600 by 600 mm. So the difference in thickness is only to compensate this effect of corrosion. So the standard has provided the formula for calculating the earth electrode resistance value. That is, here we are explaining about this electrolytic resistance, and it is not this ohmic resistance. So the resistance of the plate earth electrode for the fault current to dissipate into the soil. If you observe this formula, it depends upon the two factors. So one, rho is the resistivity of the soil, and second one, area is the surface area. So if you take area, there are two areas are there. One is surface area, another one is cross-section area. But for this earth electrode resistance value, we will be considering the surface area of the material, because the current will be dissipating from the surface of the material into the soil. So here we will be considering the surface area. So if you consider the surface area will be depending upon the length and width. So if you consider in our case, the surface area will be depending upon the length and width, and it won't depend upon the thickness of the material. So the surface area does not depend upon the thickness. So if I perform the calculation for cast iron pipe or GI pipe or copper pipe, then I will be arriving at the same resistance value irrespective of the thickness. So the thickness is provided only to compensate the corrosion effect. So in this formula, we can observe that the resistance value does not depend upon the material and its resistivity, whereas it depends only on the resistivity of the soil and the square root, that is surface area. So the resistance mainly depends on the surface area and resistivity, and does not depend upon the material of the earth electrode. So this is the formula for calculating the resistance value of pipe and rod earth electrodes. So if you observe this, in this formula, there are three different parameters. The first one is rho, that is resistivity of the soil, and second one is the length of the earth electrode, and third one is the diameter. So in this formula also, if you observe, the resistance value does not depend upon the material. So if I use either copper pipe or GI pipe or stainless steel pipe or a copper coated pipe or rod, so if the length and the diameter is same, the resistance value will be the same, and the resistance value does not depend upon the material of the earth electrode. So if I am using the strip as an earth electrode, here also, if you observe, the formula depends upon only three parameters. One is rho, L, and D. So here also the resistance value does not depend upon the material of the strip. Whether if I am using either copper strip or GA strip, the resistance value will not be affected. Only the lifetime of the earth electrode will be affected because of the corrosion property. So if you consider all these three formula, we can conclude that the earth electrode resistance value does not depend upon the material, whereas it depends on the resistivity of the soil and the dimensions of the earth electrode. So, in earlier slide while explaining, I mentioned that for some specific applications, many people will be asking, what should be that, how can we reduce the earth electrode resistance value? So, if you take this earth electrode resistance value from the previous formula, we can observe that it mainly depends upon the soil resistivity, and other two parameters are length and diameter. So, if for one specific site conditions, I cannot change the soil resistivity value, but I can increase the length and I can increase the diameter. So by increasing the length and diameter, I can reduce the earth electrode resistance. Also, by providing parallel connection of multiple earth electrodes, I can reduce this earth electrode resistance value. And in the previous first slide, we have shown that the dissipation, the potential drop will be very much higher in areas very near to this earth electrode. So by providing artificial treatment, that is by providing earth enhancing compounds, I can reduce the earth electrode resistance value. And the soil resistivity mainly depends upon moisture content and the soil content. Therefore, by increasing the moisture content and soil content, I can reduce the earth resistance to some extent. So these are the points which we can use for reducing the earth electrode resistance value. So if I am going for this parallel connection of earthing, so we might have seen about this in circuits, if 3 or 4 resistors are connected in parallel. So if I consider R1, R2 and R3. So if I consider R1 and R2, R3 are equal, so in that case, the combined resistance value or effective can be calculated by dividing this by 3. For R equal to R, then the effective value will definitely be R by 3. But we cannot use the same application for earthing, because here all the resistors which we are mentioning are ohmic resistance value. But in our case, we are explaining about this electrolytic resistance. Here, the conduction mainly takes place on only one material itself. There is no interference of other medium. So the current is flowing means the current is flowing on that particular material alone, and this resistance is specific to that particular material. But in our case, the current is discharging from one medium to another medium. So we cannot apply the same method for finding the combined resistance value of multiple earth electrodes. So if I am installing 4 or 5 earth electrodes in particular site, then I cannot find the earth electrode resistance value of one earth pit, and I cannot divide that earth resistance value by 4 to find the combined resistance value of 4 earth electrodes. So here one of the important parameters in the finding the combined resistance value is the spacing. So proper spacing should be provided between the two earth electrodes. So if in case I am installing these two earth electrodes very close to each other, for example, if I am installing at a distance of 0.5 meter, so in this case, if any fault current is discharging, then I am interconnecting these two earth electrodes. So here, these two earth electrodes are the same potential, and since they are at the same potential, the discharge can happen only on 50%, and here also the discharge will happen only on another half. In this in-between area, the discharge will be very much poor because there will be an overlap. Here it will be overlap. So because of this overlap, in this in-between region, the conduction won't be happening. I am by providing a lower spacing between these two earth electrodes, I am reducing the performance of this one earth electrode. So proper spacing between these two earth electrodes plays a crucial role. So I need to provide proper spacing between these two earth electrodes. So if I take this alpha value, it mainly depends upon the spacing. So if you consider this, it is inversely proportional. So if I increase the spacing, then the value will be reducing. So based on the spacing between these two earth electrodes, their combined resistance value will be differing. So for example, if I install 4 earth electrodes, if I am providing only 3 meter spacing, then in that case, the value will be little higher. So if you take the same example, if I am providing 4 earth electrodes and if I am providing a spacing of 6 meters, so in this case, the value of this combined resistance will be lower than the spacing of 3 meters. So by increasing the spacing, I can reduce the earth electrode resistance. So the standard has explained about two different configurations. One is linear or straight line configuration, another one is hollow sphere configurations. So in this hollow sphere configuration, the earth electrode will be placed on the side of a hollow square. In linear, it will be placed on a straight line. So this is the formula for calculating the combined resistance value. I cannot go for R by 3 or R by 4, which we generally use for analyzing the circuits here, because in circuits we will be explaining about this ohmic resistance, but here we will be explaining about this electrolytic resistance. So the formula which we use for electronic circuits cannot be used for earthing. So this is how the spacing has an impact on the utilization. So if you can, in this case, because of the improper spacing, there occurs an overlapping. Because of this overlapping, the performance of electrode will be reduced. So the standard has mentioned that the minimum spacing should be equal to the length of the electrode. So if I'm using 3 meter electrode, then the minimum spacing should be 3 meter, but we can go up to twice the length of the electrode. So if you take this as an example, here the length of the electrode is 10 feet. So we can go up to twice the length. But nowadays we don't have that much of spacing. So nowadays many people are normally going for this minimum requirements, like minimum spacing should be equal to the length. So the distance between these two electrodes should be minimum of 10 feet. So this is the minimum requirements. Because based on the spacing, the earth electrode resistance value will be varying. So the second important thing in selecting this material for earth electrode resistance is the current carrying capacity. So if the proper conductor sizing is not chosen, then the material will get damaged because of excessive heating. So if any current flows through any material, heat will be developed because of this I squared R. So every material will be having its own resistance, and based on this current flowing, the heat will be produced, and if the heat is much higher, then the material itself will melt. So the standard has provided the formula for calculating the current withstand capacity of any materials. So if you take this as an example, S is the cross section area. So from this we can derive that current will be S into K divided by root of T, where T is the time period. So if you take normal people as an example, so if you give me 5 kgs of weight, I can hold it for 5 minutes. At the same time, if you give me 50 kgs of weight, I can hold it only for 1 second. So if the weight is increasing, obviously the time period of holding will be reducing. The same is applicable for the conductor as well. So if I providing more current, then the time of withstand will be reducing. So the factor K depends upon the time as well. So the value of K will be depending on the duration also. So for 1 second it will be 205, whereas for 3 seconds it will be 118. So the current carrying capacity of any material will be higher for 1 second and it will be lower for 3 seconds. So if one material can handle 15 kA for 1 second, means it can handle for 1 second only, and if the duration is increasing, it may not be able to handle. So the duration plays a crucial role in the current carrying capacity of the material. So the standard has provided the value of K for different materials. So this is the table from IS 3043. So IS 3043 has provided the formula and the factors used for this formula. So we have provided some examples for this calculations. So if you observe this, they have provided the calculation for 25 by 3 mm strip. So in this case, the formula is I will be S, that is the cross-sectional area of the material into K divided by root T, that is the formula. So here, if I am using 25 by 3 mm, so the cross-sectional area will be 25 into 3, which will be 75. So the cross-sectional area will be 75 mm square, and The K depends upon the material and the duration. So since it is 1 second, I am taking 205. So for 3 seconds, it will be 108. So if I consider this, the current carrying capacity of 25 by 3 mm strip for a period of 1 second will be 15 Ka. So if it is 3 seconds, then it can carry only 9.5 Ka. So based upon the material and the duration, the current carrying capacity will be varying. So I have to perform this calculation and I have to choose the material accordingly. And one more thing is the corrosion will be coming into the picture. So if you take the copper, the corrosion rate will be much lower. So if you take any plant as an example, if the lifetime of the plant is 20 years, then the current carrying capacity of the conductors at the end of 20 years should be able to carry the fault current. So while selecting this material, I have to consider a factor of corrosion as well. I have to increase the conductor sizing so that at the end of 20 years, this material will be able to withstand the fault current without any damages. So if you take this pipe as an example, the conduction will be taking place only on the thickness. So it won't be happening on the inside because the inside area will be hollow. So the conduction will be taking place only on this thickness alone. So accordingly, we have to perform the calculations. And if you take a rod as an example, we can tell that for 14 mm rod or 17 mm rod, this much will be the fault current with this withstand capacity. But if you take this pipe, we cannot go for the generalized method because if you take the pipe, there are three different classes: class A, class B, and class C, depending upon the thickness of the material. So for class A, the thickness will be lower, and class C thickness will be higher. So if the thickness is higher, current carrying capacity will be higher. So for 48 mm as an example, we cannot generally provide current carrying capacity of 48. Rather, we have to provide the 48 current carrying capacity of 48 mm via class A pipe, class B pipe, and class C pipe, because all this pipe will be having different fault current carrying capacity. So if we take this class A as an example, so for class A pipe, the thickness is 2.5, 2.9 mm, and the current carrying capacity is coming as 32 Ka. Similarly, for class B, the thickness is 3.2 and the thickness is 36 Ka. And class C, the thickness is 4 mm and current carrying capacity coming at 44 A. So because depending upon the thickness, the current carrying capacity of the pipe will be increasing. And one more thing which we have to note down in this formula is the final temperature. So whenever current flows through any material, heat will be produced. So in this case, if I am taking class B as an example, so the final temperature, if a 36 K current flow will be going, will be 500 degrees centigrade. So if we are working with any explosive storage materials area where the increase in temperature is not recommended, then the current carrying capacity has to be reduced, because in this case, if 36 Ka current flows means finally the temperature will be around 500 degrees centigrade, which is not acceptable in hazardous area. So the standard has clearly mentioned the restrictions for hazardous area. So for hazardous area, the final temperature will be only 200 degrees centigrade. So since I am restricting this final temperature, the current carrying capacity of the material also will be reducing. So for the same material, the current carrying capacity will be different for safe area and hazardous area because of the difference in final temperature. So I have to consider these many parameters into consideration for designing the proper material for the particular site. So I cannot randomly select the material. I have to perform this much of calculations for finding the suitable conductor sizing. So nowadays many people are commonly going for copper bonded rod. So UL467 has provided the formula for calculating the carrying capacity of copper bonded rods as well. So using this formula, I can calculate the current carrying capacity of copper bonded rods. So the specialty of UL467 is this testing methods is very stringent. So the first thing is the thickness. So the thickness of the material should be greater than 254 microns. That is 250 microns. So that is the most important thing. It is not the average thickness, it is the minimum thickness. And second one is, the most important thing is the bend test. So they will intentionally bend this earth electrode to some angle and they will check whether there are any cracks due to this bend. during transportation or during mishandling, if there occurs any bend, then the corrosion at that particular point will be high. So in order to avoid that, they will intentionally bend the earth electrode and they will test for any cracks on that particular bend. And third one is the adhesion of coating. So in this test, they will hammer the earth electrode into a wedge and they will check the peel off of copper coating. So the peel off should be at that local point, and in other areas it should not peel off. The copper coating should be intact. So based on this, since they are performing this method of stringent testing, the UL467, if your any earth electrode is certified with UL467, means the quality will be superior, and the current carrying capacity of the copper coated earth electrodes mainly depends upon purity of copper and how the coating is bonded. So if copper is not bonded properly, means because of this huge temperature rise, the coating will get peeled off during this short circuit test. So the copper coating and the addition of coating on this core material plays a crucial role in determining the current carrying capacity of copper bonded rods. So the second important compound is the earth enhancing compound. So in earth enhancing compound, we will be replacing the highly resistive compound with highly conductive material. So the earth enhancing compound will be highly conductive material. So many people will be asking, so if the resistance is much higher, then I will be going for earth enhancing compound. It is providing the low resistance value. But in my case, if the soil resistivity itself will be much lower. So if the soil resistivity itself is much lower, then what is the need for going for this earth electrode resistance, that is earth enhancing compound? So if the soil resistivity is lower, then the corrosion will be much higher, because the soil resistivity is lower, which means that minerals and salt in that particular soil content is much higher. So because of this huge content of minerals and salt, the corrosion will be much higher. So by providing this earth enhancing compound, we are avoiding the direct contact of earth electrode with the soil. So in such applications, this earth enhancing compound protects this earth electrode from the corrosion. So the earth enhancing compound solves two purposes. So first purpose is it replaces the highly resistive soil by highly conductive material, and second part is it protects the earth electrode from corrosion in low soil resistivity areas. So these are the two purposes of providing earth enhancing compounds. And since we are directly dumping this earth enhancing compound into the soil, it should not pollute the groundwater. At the same time, it should not pollute the soil as well. So these are the characteristics of earth enhancing compound. So it should be chemically inert and it should not pollute the environment. And the most important thing is we have to provide low resistivity. So in order to provide low resistivity, we should not corrode this material. So it should not be more corrosive. So, and fourth one is the resistivity mainly depends upon the moisture content in the soil. So it should be able to absorb the moisture and it should be able to withstand the moisture for a longer period. So these are some of the characteristics of earth enhancing compound. So while preparing this earth enhancing compound, we should make the composition in such a way that it should not pollute this environment. So since we are directly dumping it into the soil, the standard has provided 4 main testing for this earth enhancing compound. So 62561-7 is a standard which explained about this 4 different testing for earth enhancing compound. So in this, the first 2 tests are related to this environment. So it should not pollute the environment. So the sulfur current content in this earth enhancing compound should be less than 2%. So if the sulfur content is more, then the compound will be considered as failure. And the second, third and fourth are related to the performance. So the third testing is nothing but determination of resistivity. So it should provide low resistivity, at the same time it should not corrode that electrode. So the third and fourth are related to the performance, whereas the first and 2 are related to the environment. So these are the tests that has to be performed for earth enhancing compound. So if we are procuring any earth enhancing compound, we should ask the vendor about this 4 different tests, and after proper examination only we need to go for this backfilling compound or earth enhancing compound, because by providing earthing, we are directly putting it inside the soil. So if rainwater passes through this material, if it contains any chemical, means that chemical will dissolve into the rainwater and it will mix with the groundwater. So proper material should be used for this earthing applications. So this is the formula provided by the standard for calculating this earth electrode resistance along with this earth enhancing compound. So in the previous formulas, we have not used the term ρC, which is the resistivity of the compound. So this is the formula for calculating the earth electrode resistance for value using this earth enhancing compound. So earth electrode resistance measurement. So the standard has provided a method called Werner's method for measuring this earth electrode resistance. So in this method, we will be injecting a current from between these two earth electrodes, that is the test electrode and the current electrode. So between these two, we will be injecting a current, and the voltage between this potential electrode and the test electrode will be measured using a voltmeter. So the ratio of voltmeter rating and the current meter rating will be giving the resistance. So this is how we will be measuring the earth electrode resistance. We need to remember that the earth electrode resistance is electrolytic in nature. So while measuring this earth electrode resistance, we are measuring the electrolytic resistance and we are not measuring the ohmic resistance. So since we need to measure the electrolytic resistance, we need to inject the current into the ground and we need to check the voltage drop. So the ratio of voltage drop and this current will be providing the resistance value. So standard has provided different methods for performing this test, and the most commonly used method is fall of potential method, that is 61.8%. So we have mentioned that there will be two probes. One is voltage probe, another one will be current probe. So the 61.8% explains about the distance of the two probes from the earth electrode. So in this case, the distance between this current probe and the earth electrode is 50 meters. And the distance between this test electrode and the potential probe is 31 meters. So this 31 meters is nothing but the 61.8% of 15 meters. So I will be placing this potential earth electrode at a spacing of 61.8 meters, 61.8% of the second earth electrode, second spike. So in this case, we will be considering 50 meters, but normally we don't have this 50 meter spacing at all. So for example, if I am placing this secondary spike at a distance of 10 meter, then the potential space should be at a distance of 6.2 meter. So that is the ratio. So the ratio of this first spike, that is potential spike, will be placed at a distance of 61.8% of the distance of current spike from the earth electrode. So this is something which is commonly used for measuring the earth electrode resistance. So there are two types of meters available. One is analog meter, another one is digital meter. In analog meter, we have to rotate the handle to inject the current, and based upon this current injected and the potential drop, it will be showing the resistance value in ohm. So these are the commonly asked questions that were related to this earthing. So first one is if we use the pipe earth electrode and plate earth electrode, whether the resistance value for pipe will be lower or plate will be lower. So we have shown this formula for pipe earthing and plate earthing. So if you perform this calculation, we can observe that for the same surface area, that the plate earthing will be having higher resistance than the pipe earthing because of the configuration. So if you take this pipe, the dissipation will be taking place in the form of concentric circles. So the dissipation will be much quicker in plate, pipe and rod configurations than the plate earthing. So because of the shape, even though if you are having the same surface area, the resistance value of pipe will be higher than the pipe earthing. So this is what explanation provided by the standard. So the second portion is effect of water. So I have shown in the table also that the moisture has a huge impact on the soil resistivity. So if I continuously pour water and increase the content of moisture in the soil, whether I can achieve this lower resistance value. So the standard has explained about this limitation also. So if the moisture content is reduced up to 20%, then it will be having a huge impact. So you can see this. So if the moisture content is 10% to 20%, there is a huge drop in the resistance value. But after this 20%, there won't be much decrease in the value. So 20% of moisture is the saturation point. After the point, there won't be any effect. So the same is applicable for salt also. So after 5% of salt, even if I increase the salt content, there won't be much effect. But if I increase the salt content continuously, it will result in corrosion. So it will reduce the lifetime of the earth electrode because the corrosion will be higher if I increase the salt content. So the salt content also has effect up to the 5%. So the 5% is the saturation point for salt. So if I continuously increase the earth electrode length, whether I will be able to achieve the target resistance. So if you observe this, the curve will be starting to saturate after 5 meters and all. So up to 6 meters, there will be a huge difference in increasing the length. And after the 60 meter, 6 meters of length of earth electrode, there will be some effect, but the reduction in resistance value will be little lower. So in some applications, if I don't have much spacing, then I can go for length greater than 6 meter also, but the effect will be little lower after 6 meter. So copper and Ga. So if you take some side condition as an example, if the earth electrode resistance value is coming higher, that is if I use Ga earth electrode, if I am getting 7 ohms of resistance. So if I use the copper earth electrode in the place of Ga earth electrode, whether I will be able to achieve this lower resistance value of less than 5 ohm, because copper is having lower resistance than the Gi. So the answer is no, because the earth electrode resistance does not depend upon the resistance of the material. So whether if I am going for copper or Gi, if the dimension is same, the resistance will be the same. So the resistance value can be reduced by increasing the length or increasing the diameter, and it cannot be reduced by changing the material, because the resistance value does not depend upon the resistivity of the material, and it does only depends upon the soil resistivity and the dimensions of the earth electrode. So by replacing this copper, it won't be any effect because the copper has very low ohmic resistance, but here we are considering this electrolytic resistance. So here the resistivity of copper and Ge won't be considered, so it won't have any impact. So we are using copper only for as a earthing material mainly because of this corrosion resistance property. So this copper has excellent corrosion resistance property than this Ge. So because of its superior corrosion resistance property, we are preferring copper as the earthing electrode. And if you take this corrosion rate, the corrosion rate of Ge is around 0.5% per year, whereas for copper it is around 0.2% per year. So because of its superior corrosion resistance property and good conduction, we are using this copper as earth electrodes. And it is we are not choosing copper only because of its lower resistance value. Here we are not considering the ohmic resistance, we are considering only this electrolytic resistance. So the conclusion is we cannot place a random size of earth electrode of 1 meter length or 2 meter length and connect it to the equipment for protecting these people from during the fault current. So earthing is not simply providing a rod or pipe for an equipment. So it involves a detailed calculation. So if I am using providing earthing for one equipment, if I am using 14 mm dia rod, I cannot use the same 14 mm dia rod for earthing the neutral of a transformer. So if you take this transformer as an example, the fault current rating has to be calculated, and based upon the fault current rating, I have to go for this suitable sizing. So if you take the copper bonded rod as an example, we have performed testing for 17 mm dia rod for 20 kA for 1 second. So if you take this 23 mm dia rod, we have performed testing for 35 kA for 1 second. So if there are any substations where the fault current rating is around 20 kA for 3 seconds, then in that case I cannot go even for 17 mm dia where it is rated for only 1 second. So based upon the fault current rating of the particular site conditions and location, I have to choose the material accordingly. So I cannot randomly select the materials. I have to select the materials as per the suitable site conditions and the application. So in the same site conditions, if I am providing earthing for one equipment body, then I can go for this 17 mm dia. And if I am providing earthing for the transformer where the fault current is coming as 30 kA or 40 kA, then I cannot use the same 17 mm dia rod for the transformer neutral. So it mainly depends upon the fault current rating at that particular location. So I cannot randomly provide the sizing of earth electrode. So proper designing has to be done for selecting this conductor. And if you take this hazardous area, the temperature has to be considered. So if I am performing this calculation, means if it is an hazardous area, I have to reduce the temperature to 200 degrees centigrade, and I have to do the calculations accordingly. And corrosion is the most important parameter to be considered for this earthing. So if the soil is having very low resistivity, which means that the corrosion will be much higher. So while selecting the materials, I have to give proper importance about this corrosion resistance property of the particular material. For low resistive areas, I have to use material having superior corrosion resistance values. And the earth electrode resistance mainly depends upon the soil resistivity, because it is electrolytic in nature, it is not ohmic resistance. In electrolytic resistance, the surrounding medium plays an important role. So here the surrounding medium is the soil. So the soil resistivity plays a crucial role in earth electrode resistance values. And if the soil resistivity is lower, the corrosion rate will be higher. So the soil resistivity and the corrosion are inversely proportional to each other. So if I want to reduce this earth electrode value to a lower value, then I can go for either multiple earth electrodes in parallel connection, or I can use this one artificial treatment of earth electrodes by using this earth enhancing compounds. So the parallel connection of earth electrodes, we cannot use the same formula which we use for electronic circuits. Here it is electrolytic in nature, so we have to use the formula provided by the standard, and we need to select the formula according to either linear configuration or this hollow square configuration. And this earth enhancing compound not only reduces this resistivity of the soil surrounding the earth electrode, it also serves another purpose by protecting this earth electrodes from the corrosion.